little bit about myself.
Sure.
Well, currently I'm the first semester student in TUM, and as for discrete structures, for me it is a bit confusing as far as I didn't have such a discipline, so this is like a new thing for me in terms of mathematics. I finished international baccalaureate program in Russia, and so yeah, so I'm not confusing with mathematics, but well, with discrete structures. So I think that this is a bit, let's say, abstract
It is.
case in mathematics. Well, so this is, I guess, why I have some confusions about this, basically.
Okay.
Yeah.
So I don't want to. I lost you. I don't want to lie. It is abstract. It is damn abstract, and oh my god, is it this one? Yes, it is. Okay. Can you see me? Yes, I can.
Yet.
Yes, you can. Yeah. Okay. So it is confusing, and yes, it is abstract. I don't know who invented this thing, linear algebra, discrete mathematics. Although, if you wish to have a look at the depths of it, there is really discrete mathematics at the bottom of the world. Because if you let me put yourself here. If you think about quantum world and all what is going on down there, we see that continuous sets and intervals are just gone. I mean, they are just not the real way, not the way world is set. I am finishing. We started 20 minutes earlier or something like that, and I am I'm still wanted by other people. Okay, yeah, a busy man. So if continuous intervals are not there, then what is there? And the answer is discrete. When you have 1 point to 1 point, or 2 points to 2 points, and so on. So I would like to go through some MCQs today. As I told you, we are going to talk about relations. By the way, what is a relation? What is a relation?
Well, so relation we can describe in different ways. Well, basically, we can say that this is a multiplication of, well, there are different relations. For example, binary relation we can represent as a multiplication of matrices of some graph matrices, yeah. And how else?
Make it easier. Make it easier.
Just how to sets can be related to each other.
Look, a relation is a selection of some pairs from an ordered set. For instance, if you have a binary product, like a Cartesian product of two sets, and I am going on the board to draw something. So we are here. Let's say we have A equals 1, 2, 3, and B equals 1, 2, 3. Can you draw A times B?
Okay.
Make it easier. Make it easier. Make it easier. Make it easier. Forget about this one. Just take 1, 2, and 1, 2 here.
1, 2, and 1, 2. Or this is 2. Okay. So. So, but well, I didn't really understand the multiplication of it. So, what should be the product? So, whether it is
well, the product of these is going to be, so the Cartesian product is going to be all the pairs that we can build here. So it is 1 1, 1 2, 2 1, 2 2. Okay. Yeah. Don't be too formal. At least not with me. So this is the total set, and now we want a relation that says parity relation, so only pairs with the same parity. What is the result of this relation? It is a subset, because we are going to pick only the pairs where both entries have the same parity. For instance, actually you do. So that. Identity. Yes, in this case it is an identity. If we had like 3 and 4, the same type of parity would give you 1 3, 2 4, and eventually the reflexive ones, so 3 1 and 4 2, except the loops, right? Okay, so this is a relation. Today we are going to investigate properties of these relations. I have some MCQs I have sent you, and I would like to go with that one first, and then in the second part of depending on how quick we are with explanations and wording, I have some exercises that I want to go through with you. These are very close to the material you sent me. It took me a couple of hours to prepare that, but I was able to do it good. This is for today. Basing on today's result, the time versus result ratio, I am going to tailor more perfectly next one, which is going to be, if I'm not mistaken, on Friday. Aren't we booked on Friday?
Not yet, I guess. Okay. We just booked this lesson, but it is okay.
Very good. Now, any question for you? If not, let's start with question 1.
Okay. In screenshots, right?
Well, the images that I sent you. Just let me.
Okay.
Let me do
just
like
paste
this.
It here. I guess. No.
No, I can't because I am lazy and I score my money more than this. So that's why I didn't yet buy the full thing of it. It may be worth it anyway. So question 1, logic.
Okay, logic. Okay, logically equivalent if A then B. Okay. So let me go here. I will just write a truth table.
Yes.
Then B. Okay, so true, false, true, false. This is true, this is false, this is true. Okay, so this is A and B, A and B. And this is the union, right? And we have this angle.
No, that's intersection.
Down.
That's intersection.
Because I thought that
the other one,
different.
this one. This one is union. It is more like a U which then comes to a V, because it's Latin, vel.
Well, I thought that this is union, this is union, this is intersection, and this is also intersection.
No, the other way around. Look. The other way around. This is intersection, this is intersection, this is union, this is union.
Oh. Okay, then I looked for in other definitions. Okay, then no problem. Okay. Again, true, false. True. And false. If this is intersection, then this is true. And others are false. Then not A union B. Here is A, here is B. True, false, true, false. So
let me tell you, very German as a way of solving. Very thorough, very German. So I'm not kidding. I'm just providing you with some vocal feedback.
Well, this one is equivalent.
So we have B, because not A vel B, and not B going to not A. So what are the two correct options here?
Yeah, D and C.
D and B.
No, not C, B. Yeah, D
very good. B. Very good. Very good. Now, let's go to quantifiers.
Okay, statement is correct. Tag for all x with R P holds. Okay, this exists. Well, I suppose that A is correct. No. If not R and no.
Or no, not.
It is incorrect.
No, it is incorrect.
No, this is not. Yeah, this is incorrect. Exists with and no, there is exists with. Result not. Okay. Well, maybe there is exist X with not R or not B, but I'm not sure.
No, the correct one here is B, because not all R of X are P of X. If and only if it exists one R of X intersected with not P of X. So B. Okay, don't worry. I prepared these MCQs to assess a little bit what is our starting point, because we have not too much time and I want to not to lose any. So power set.
Okay. I suppose that in power set, so I just forgot. We have partitions now. Okay, so let's say.
And we are looking for, yes, module of 2 to the a power. So what is the cardinality of this power set?
All the partitions and like if we have the power set, then here we will have something like this. One, two, 1, 3, 2, 3, and 1, 2, 3. Did I miss something?
No.
No.
Well, the only thing that I could point out is that I wouldn't, when you include this one, there is no 0 here. So we may miss one of the properties.
Oh, well, but this is not 0. This is like yeah.
Anyway.
Okay. So in this case, 3 is 7. Oh no, this is 8.
Yes. And how did we get it? Because it is 2 to the 3rd power, where 3 is actually here. Very good.
So just 2 in the power of cardinality of our A.
Exactly. 2 to the power to the cardinality power, and you get 2 to the power of A. Very good. Set difference.
Okay. So let A equal 1, 2, 3. B equal 2, 3, 4. And we need to know A without B. Well, so basically this is the same as A intersection with not B.
Yes.
And here we have for the intersection this one, this one, this one, this one. So this is just 1.
Exactly. So elements that are in A but are not in anti-B. I use this anti part. Question 5. Relations reflexivity. Oh, by the way, quickly, what is reflexivity? What does it mean?
Well, when we have, for example, AB, then we should have BA in each, let's say that not directions, but still from.
Be careful. Be careful. Not only about pairs, but reflexivity means. Let me write it here. So reflexivity, means that each element is linked to itself. So we have loops.
Yeah, also.
Can you make an example of mathematical operator?
Which does this reflexivity?
Yes, which is reflexive.
A mathematical operator, in basic mathematics, or?
Yeah, in basic mathematics.
I suppose it can be power. But no, not power, but...
No, another one.
Close to the same element.
Well, the answer is this one. Lesser or equal. Because 3 is lesser or equal than 3, and an example where we don't have it, it is, for instance, 5 is not lesser than 5.
Okay.
Okay. So let's get back to our relations reflexivity.
Consider relation A, B, B. Which property does R satisfy? Well, yeah, reflexivity, as far as we have each element pointing on itself. So A, B, it's not transitive, so we do not have a C.
Exactly. So we don't have a two steps chain.
Yeah. And as for symmetry, well, let's say that this is A, this is B, this is C. So we have this, and we have a B. Antisymmetric.
Exactly. And how can we say that? Well, look, I mean, A is there, B is there, C is there, so this is reflexive. What about symmetric? Well, there is not BA, and this leads you to think that AB is there, but BA is not. Hence, okay. About the transitivity, there is AB, but nothing about B something else. So there is no closure, because we can't go further from B anywhere. Good. 6. Symmetry.
So, symmetry. Which of the following relations on 1, 2 is symmetric? So B and D.
Not only, because you have B and D, of course. So 1, 2, 1, 2.
And C also.
Exactly. Maybe. 2, 1 is there. But whenever we find 1, 1, it includes 1, 1. And 1, 1 again is there. So B, C, and D. Very good. Transitivity.
Okay. Which must be true for transitive relation. If A, B, and BC are in R, then AC is in R. If AC is in R, then A and BC are in R. A.
Correct. A and only A.
Yeah.
And then we have the last one.
Okay, which combinations of properties characterizes as an equivalence relations? Or, yeah, I suppose there are three of them. So equivalence relations, I guess, symmetric, reflexive, and transitive, because antisymmetric, this is for partial order.
Exactly. Very good. Very good. Very good. Okay, so a quick feedback on what we did up to now. How, I mean, is the difficulty level what you are expecting of? Is my report to you pleasant? Are you, I mean, what is the first feedback?
From me?
Yes.
Well, I think that this, as for tasks, well, that wasn't so hard, but well, yeah, I
not yet
still, let's say, gained the more easier steps how to solve some of these tasks. Yeah.
As far as I can tell you, as a quick feedback, I see you are unsure. I see you are tentative in several parts, which is not good and not bad, but this is something that we may want to work on. So that said, let's go to the a little bit more complicated MCQs, and here I want you and I to work on the theory behind it. So for instance, take the set where you have let R, question 1, you know, let R be an included subset of A times A. Which statement, you have it on the PDF that I sent you. Which statement is equivalent to R is symmetric?
I guess B.
B.
R is equal to
yes.
R in the power of C. I forgot that. Not transitive, but
transposed.
Transposed graph. Yeah.
Okay. So whenever you have that R is an included subset of RT, and RT is an included subset of R, then they must be, of course, equal. Very good. Very good. Mutual inclusion is the strongest, so only fully equivalent is the correct formulation. MCQ number 2, antisymmetric versus asymmetric. Which implication is always true? Let's discuss a little. Let's break the theory down. So antisymmetric means what? That if the pair AB belongs to R, then what can you say?
Well, then BA is not included in R.
Yes. So we can write it quickly. You can do that, I can do it.
No, okay.
Okay. What is automatically included in this statement? Actually implied, not included, implied. Irreflexivity. Irreflexibility. Why that?
Because, well, if we have AA, this is exactly. That doesn't matter
exactly
how we
transpose it. Belonging to R would violate asymmetry.
Yeah.
Would violate. Oh, by the way, I don't know whether you are a fan of paper devices. You are more than happy to take notes over our chat, and after send me pictures. I want to check what goes there in your mind so that, you know, I can base on those notes to prepare next lesson.
Okay.
Okay. Now, antisymmetric is way weaker. By the way, this is asymmetric, not antisymmetric. Asymmetric. Antisymmetric. So antisymmetric is way weaker, and so we can state that if AB and BA belong to R, then A equal B. And asymmetry, from this point on, asymmetry forbids all the two-way edges, including diagonal ones. So let's say that this one, I am writing it anyway. Actually, I'm going to text it because it's going to be quicker. Text here. So, what is it? Text. So asymmetry forbids two-way edges with diagonal. So trivially satisfies antisymmetry. So what can we, you know, infer? We can infer that from asymmetry we can infer anti-symmetry, but the contrary is not. Okay. Trivially satisfies antisymmetry.
Antisymmetry from these two edges. Diagonal terms.
Okay. What statement is equivalent to R is transitive?
One moment.
Yes, please. Take your time. I'm going to pour some coffee in the meantime.
Okay, so reflexive and not states. Which statement is equivalent to R is transitive? A.
Are you sure?
No.
Let's have a look at the following. Let's break it down. So A, B, and BC. What is transitivity? Belong to R. To R. consequence that AC belongs to R. Now let's think about relational composition, which is RR. What is this? It is the set of all pairs AC such that exists B according to which AB included in R forces BC included in R. So this is the relational composition. So in this way, transitivity if and only if all pairs are already in R. So R included in R. Okay, hold on a second, please. Okay, like this. Good. Satisfied with the explanation?
Yep.
Great. Let's go on. Antisymmetric condition for partial orders. Antisymmetric condition. So which condition must hold for every partial order R on A?
So it should be antisymmetric, antisymmetric, transitive, and reflexive. So not reflexive, not reflexive.
Reflexive. So for being reflexive, what does it mean? It means that the identity on A belongs fully to R, right? Then we have antisymmetric, and we know that because we have just said that, but the more I write, repetita juvent, and there is this Russian version which is повторение мать скуки, isn't it? Oh no, vyuchenia, well, doesn't matter. So BA belonging to R if and only if A equals B. Okay, and then oh, by the way, what is the equivalent of this one? The equivalent of this one is that R intersected R transposed is the identity. So the only common element between the relation and its transposed is the identical one. And the third one, it must be transitive. Very good. So the transitive, which we have seen before, RR must be self-sub included. So for all this, we can state that the correct answer is B, which is R included RT, R intersected RT is included in IDA. Now, give me a very quick break. Just a second. I'll open to my cat and I will be right back.
Mm-hmm.
Okay, sorry, I'm back. Okay, next one. Constructing an equivalence relation. Which construction always produces a hey, say hello. Gata, say hello. Hello. Okay, go there and be quiet.
Okay.
Which construction always produces an equivalence relation? So R closed R plus united IDA R united RT
okay.
And R united RT closed.
Okay. So basically the first one and the second one are equal. So, and we need, so for equivalence relation.
Yes.
For equivalence relation, we need reflexivity, symmetry, and transitivity.
Yes.
And that means, I guess, D.
Yes, exactly. D. And by the way, this is clearly stated in one of your, I don't remember which sheet, but it is clearly stated there. So that's why I wanted to give it a try here. Very good. Very good. Now, strict weak ordering. Which correctly characterizes a strict weak ordering?
This is what I need to think of, because
think about
I
it.
didn't really remember.
Okay. You know, when you are in, okay, forget about it. Just bear with me. Sometimes we may be cat disturbed or children disturbed. So, strict weak ordering, we have, strict weak ordering needs to be asymmetric, which means on its own irreflexive, and orientation consistent. It must be transitive.
Sorry, what is after irreflexive?
Let me text it. Sorry, let me text it. I have the keyboard. It's just I love handwriting. So antisymmetric means must be irreflexive and orientation consistent.
What What does orientation consistent mean?
Arrows just on one side.
Ah, okay. Okay.
Okay. It must be transitive and must hold an incomparability relation. So we have I being the set of all A, B pairs such that if A, B doesn't belong to R, then B, A doesn't belong to R. Like this. What is the difference between strict total orders? So strict orders have the incomparability relation only relates to identical elements.
Mm-hmm. So basically identity.
Yes.
Uh-huh. Okay.
So if A is not included, then AA is not included, of course. Inclusion monotonicity of closure. For any couple of relations, if R star is included in S star, then R included in S. Or if R is included in S, then R star is included in S star. Then we have R included in S transposed. And the last one, R included S, then R plus equals S plus. You may want to discuss on this.
Mm-hmm. Okay. So this is not strict orders. This is I need to write the name of it. I'm sorry.
Yes, please.
For these properties, which property they describe again?
Well, let's not at the moment break down into the single properties. This is something that eats up time. You know, that's just academicity, which I don't want. I prefer to develop critical thinking. So the what we are looking for is the monotonicity of the star operator.
Okay. Well, basically, I see that from the second, well, let's say property, yeah?
Yes.
So goes the fourth one, as far as R star is the union of identity and R plus.
Yes.
So hence we can describe it like that. The fourth property goes from the second one, and so R plus is the I want to say partitions, but I don't know whether it is correct. Well, like if we have our star, so this is basically our union R, and so we will like unite.
Yes, all the powers.
R's, like the cardinality of R, so the number of elements matters in this case, as well as with S plus, etc. So if they say that R is a subset of S,
then R star is a subset of S star.
Yeah. I think I need just an example, because I do not really understand how they can be really related, because a subset may have less amount of
less or the same
elements.
Less or the same.
Less or the same, yeah, right.
Okay. Well, after we make a very small break, I can provide you with an example of this. So let me write it here, example. Okay. So if you are satisfied with MCQs, forget about 8 and 9. Just I'm getting tired of MCQs, and I would like better to spend the last half an hour on worked exercises. I mean, we pick an example and we work through it.
Yep. Okay.
Now, exercise 1. So I didn't send you this, so you gotta follow what I write here. So let A be 1, 2, 3, and a relationship R given by the following table. So it is 1 if the element is in R, and returns 0 if it is not in R. And the table is the following. So it is 1, 2, 3, 1, 2, 3, and we are given by 1, 1, 0, 0, 1, 1, and 0, 0, 1. Well, now the question is always the same. Interpret and decide whether this is reflexive, symmetric, antisymmetric, transitive, and all the rest.
Okay.
And I would like to work it out for the first exercise, so that I give you, I don't know, like a template of steps, and then you are, we are going to see the next one. So solution. First one, write R as set of ordered pairs. So from the table we have row 1, we have 1 1 and 1 2. From row 2 we have 2 2 and 2 3, and for row 3 we have only 3 3, right? So can we now compile the relationship in the set view? Of course we can, because we have 1 1 1 2 2 2 2 3 3 3. So this is our relation as interpreted from the matrix, from the table view. Good. Now, step 2. Is it reflexive?
Yep.
Whatever, we check if the pair AA belongs to R for each A, and we have 1 1 2 2 and 3 3 belonging to R, so it is symmetric. Sorry, reflexive. Step 3, symmetric. How do we check symmetry? Well, we check for any couple AB, does BA appear? So we have a look at the couple 1 2. Does it force 2 1 to belong to R?
No.
Exactly. So it is not symmetric. Now that we see that it is not symmetric, we go for step 4. What about antisymmetry? So if
it holds.
If A is different from B and AB and the couple AB BA belong to R, then A equals B. But in our case, there is no pair with both directions except for diagonals. No pairs with double arrows except diagonals. So what is the conclusion? There is no violation, hence it is antisymmetric. And finally, step 5. Is it transitive?
So if we have
we must check chains A, B, B, C, and here we have 1 2 and 2 3.
2 and 2 3. Yeah, we have a chain.
Is 1 3 within R? And the answer is no, it isn't. So no transitive. So what is the final classification? It is reflexive, it is antisymmetric, and how can we classify it? It is a non-transitive preorder and not a partial order. Not a partial order. Now, exercise 2. Let me get back here. Like this. So, exercise 2. Let A be the set of 4 elements, A, B, C, D, something like that, and R defined by the directed graph, so the D graph, A, B, B, C, C, D, A, D, and D, D. Classify.
Okay. So R is not reflexive, as far as we do not have. No, we have one, but we do not have
the others,
all the
so
elements.
It is not reflexive.
Yeah. So we do not have AA, BB, and CC.
Exactly.
So hence it's not reflexive.
Let me write it.
Then.
So it is. Only a moment, please. 60 è troppo grande, qua, contour, oh cazzo, eccolo qua. So it is not reflexive. Let me write it here. No AA, BB, CC, only DD. Okay. Symmetry.
This graph is not symmetric as far as we do not have another direction. So from elements, so for example, from BC we cannot do CB.
Exactly.
Yeah,
so
etc.
Is o any arrow mirrored? And for instance, B going to A, B going to A, not there. So it is not symmetric. Not
here,
symmetric.
antisymmetry holds.
Antisymmetry holds. Correct. Check all reachable chains.
So we have AD, but we do not have BD.
And by the way, we don't have AC.
Yeah, and AC.
Very good, very good. I'm satisfied you did it thoroughly, correctly, and quick. Exercise 3. Exercise 3. So let A be 1, 2, 3, and R given by a nice matrix And the task is compute r squared equals r using Boolean matrix multiplication.
So Boolean matrix multiplication differs from algebra. Or it can be the same.
Can, but different names luckily relate to different objects.
Well, I just don't know. Okay. So can I just do a row by column multiplication of a matrix, so basic multiplication of matrix?
Look.
Here.
Well, okay, do that.
Okay. Well. So, row by column. So.
So very good. This is mr squared, this one here. Okay. Now let's check transitivity quickly. For r squared, transitivity requires that r squared must be a subset of r.
No, it is not.
And it is not. Because, for instance, 1, 3 is in R, but is not. Is in R squared, but is not in R. So R is not transitive. Very good. I am really satisfied. We are going really quick, and I'm happy of this. Exercise 4. Let be the usual 1, 2, 3, and construct a relation which is symmetric, not reflexive, and not transitive.
Okay, so I should write the relation, right? Such that this. Okay. Well, I guess it is easier to do with with a table, let's say so. So for example, we have elements 1, 2, 3, 1, 2, 3, other side, right? And so for symmetry, we should have AB and BA.
Yes.
Which holds non-reflexive. Well, each element should be pointing on itself, and for transitivity, we should have a chain.
It must not be. It must not be
in this case,
reflexivity.
Yeah. Basically, we can say that okay, let it be 1, 2. So we will put zeros on the diagonal. Here, and
then
2, 3.
Break transitivity.
Yeah. We shouldn't have, I guess.
So make a chain ARB and then BRC and then remove ARC.
Yeah, so for example, 1, 2, 3, let's do it like this. Transitive is like that, so we shouldn't have basically 1, 2, 1, 3. So 1, 3 is incorrect.
Okay.
And as for 2, 3, I guess it is also incorrect. No. Well, we should have only one element that will break the chain. So if we will put here 2 and 3, there will be no change. So as far as we don't have 1, 2, 3, so
yes, so we can we can put one of the two, so like 2, 3, 2 or 2, 3. But since it is reflexive, it is symmetric. Sorry, it must have the 3, 2 as well. So yes, this is correct. Excellent. Please notice that we are speeding up during this very lesson. I don't know if you are noticing that. I am. Now, exercise 5. Partial order that is not total. So let A, B, C. I construct a relation that is reflexive, antisymmetric, transitive, but not total. So the typical example is that one branch leaves 2 elements unrelated. For instance, we can go for A, B, C, so that we grant reflexivity, and then we take AB. So, do you like this?
Well, there is no AC, so this is not transitive in that case. No, CA, or it is AA, the first element,
It is AA,
right?
yes.
Okay, well, there is no AC, so this is not a transitive.
Right. I see that you are paying attention, and this is very good. Now, is it total?
Antisymmetry holds here. Reflexive holds.
But compare B and C. There is no pair within R. So it is not total.
Ah, okay.
Okay. Now I would go for the last exercise. In the last minute, I would like, some meta discussion. Exercise 6. So let A be 0, 1, 2, 3, and R be 0, 0, 1, 1, 2, 2, 3, 3, 0, 1, 1, 0, and then 1, 2, 2, 3, 1, 3. I don't want to put all the brackets, so I guess that's not a problem. Classify all 4 properties. And you go on for this one.
Okay. So this is reflexive.
Because all AA are present.
Yeah.
Yes.
Yeah. Then
let me write
0,
it here.
1, 1, 0.
Symmetry.
Not a symmetric because we do not have 2, 1.
Exactly.
In this case.
2, 1 is missing. Good. Antisymmetric.
Well, as far as we have elements pointing to in another direction, antisymmetry do not hold.
Okay.
Because we have what do we have here? 0, 1 and 1, 0, so it breaks our
antisymmetry. Yes.
Yeah.
What about transitivity?
So the graph. It's not transitive as far as we don't have 0, 3.
Exactly. Or 0, 2, by the way.
Yeah.
So 0, 2 is not there. 0, 3 is not there. Hence, no transitivity. So it is reflexive, not symmetric, not antisymmetric, and not transitive. And happily saying, you were able to solve this very exercise in really little time. While at the beginning of the lesson, I saw you very tentative on several of the properties of relations. So, as far as I am concerned, this is the material that I prepared for today. I have some homeworks, but I will send in a while, like half an hour from now. Well, what have I got to say? At the beginning of our lesson, I saw you pretty weak, and at the end of our session, I saw you landed, at least. I don't want to say strong, because otherwise you can tell me, okay, then bye-bye for the other lessons, and this is business. But I measured the change in your confidentiality and confidence. So, feedback from you, please.
Well, I started understand better this topic, so Yeah, this is very good because, well, here I see the logic, because in our university still we have a problem. So, for example, we have exercise sessions and we have like lectures, and to understand a professor from lectures sometimes is harder, and on exercise sessions, when I ask some tutors about why do we have this, for example, thing, so they just say that we learned it by heart, but well, this is not the approach in mathematics, I guess. So